All right, kids, this will be our last video dealing with what's called fluid statics. That means the liquid isn't moving, okay? Once it's in equilibrium. Now, a couple things. One, when I put a zucchini in an aquarium and tell you to do math with that zucchini in the aquarium, do math with the zucchini in the aquarium, all right? I did that on purpose. I grew that zucchini all by myself. I picked it all by myself, and I put it in the aquarium for you. And you guys didn't do the math with it. When I tell you to answer 3 questions about a zucchini in an aquarium, answer 3 questions about a zucchini in an aquarium. All right? So you all know who you are. There was one of you that answered those 3 questions. Thank you. The other ones of you need to go back to the density and pressure homework and answer the questions I told you about Abe Lincoln, the penny at the bottom of the aquarium, telling if it can notice the added weight of the zucchini floating in it. All right? Do you even watch videos, bro? Huh? I'm making these videos for you. You gotta watch them. And you have to do the things I tell you. All right? I know you think zucchinis ain't got nothing to do with physics. But physics is all about thinking, people. It's thinking. It's visualizing things. It's looking at one thing. It's seeing something else. It's making connections. Okay? It is not something you can memorize. And how many of you Googled the density of a watermelon? Really? Google doesn't make you smart, kid. All right? It doesn't. Looking at the word watermelon and recognizing that the root word in watermelon, or the main ingredient in a watermelon, is, I don't know, water. So the density of a watermelon is probably ish the same as, I don't know, water. So it will probably float with the majority of it below the surface and a little bit of it right there at the surface. Okay? What if I were to chuck a water balloon into the swimming pool? What would it do? Please don't Google. I mean, I don't blame you, but Google doesn't make you smart, kids. It makes you stupid. Okay? Please remember that. My favorite things in the world to do is come up with stuff you can't Google. All right? Now, with that, you're all going to rewatch the video because you obviously didn't watch the whole thing about the zucchini in the aquarium and re-answer those questions. For gosh sakes. What I'm going to do now is an activity with the same aquarium. And it's called Guess Your Apparent Weight. All right? And it's basically the same thing as if you go to carnivals and some dude guesses how much you weigh, and then you stand on a scale, and if you're within a couple pounds, they give you a stuffed animal or something. I don't know. It's the same thing. What I'm going to do is an example with this little piece of metal here. It's aluminum. It doesn't matter. But you guys know if I suspend this, it'll register its weight in the string. That's its force of tension. That's its support force. Sometimes we call it a normal force. Sometimes we call it a tension. If I put this object underwater, then the buoyant force helps push it up. So the tension will decrease because the water is helping this item hold it up. And so your job is to predict what the tension force will be when I hold this object in that aquarium that no longer has the zucchini in it. All right. First thing I'm going to do is show you the scale that we've used a few times before. So this object I will point down to the scale right there, zero it. I'm going to put this guy on a scale. Boom. You can see it's what, 123.7. All right, 123.7. So what I'm going to do is obviously write that down. 123.70. That's grams. Okay. Now what I'm going to do, or 7, why me, hell, it don't matter, is move this over to that right there. That is what the scale reads once I put that funny shaped piece of metal on the scale. Boom, you read that, that's what it says. First thing I will remind you, that is not a weight, that is a mass. So when I draw the arrows acting on this guy, boom, this is the force of gravity, which is m times g. Okay? Something else I'll remind you is scales are stupid. They do not know with how much force something is being pushed onto them. The only thing this scale knows is how much force it has to push upwards with in order to support that. And that arrow will be drawn like this, and it's labeled an Fn. Scales do not tell you your weight, they tell you the normal force. Okay, now when it's on a nice flat level surface, you can say the sum of the forces in the y equals may, and since it's not moving, may goes away, it drops to 0. There is a positive normal and a negative gravity, and it once again equals the number of days I've been to school this year. The Fn is what the scale will read. It is equal to Fg in this example. Okay? Fg, we said, is equal to mg. Now what I'm going to do is show you how to go from 123.7 grams into a force to mg. All right? Now, what we're going to do is rewrite that number, 123. Now, this m, you all know, though, needs to be in kgs. You know that, right? So this has to be in kg. Well, this is 123.7 Gs. Hopefully, you already know you need to move that decimal point 3 places. Tree, you got to know how to count to 3 to go from grams to kilograms. And it's going to be a smaller number. So 123.7 grams is the same thing as 0.1237 kgs. All right. Now, I'm going to multiply that by 9.8. That's meters per second squared. And you can do that ish in your head. 9.8 is dancing around 10, isn't it? Which means the decimal point I just moved over 3 places. As soon as I multiply it by 10, I'm going to move it 1 more place back. So this ought to equal 1.23, if you want to call it 7, 1.237, it's okay. 1.24 is more than enough. This is, whoops, that'll say newtons, 1.24 newtons, kilogram meters per second squared. All right? Which, again, the reason I'm reminding you that is you got to know the skill to go from grams to kilograms and kilograms to newtons. And in this case, 1.23 grams, all you got to do is move the decimal point 2 places to get it to newtons. Now, it's not going to be exact because that's a 9.8 instead of a 10. But when I hold that item up using a magic force-ometer, okay, it should register a number dancing around 1.23, maybe a little off. But what I want you to look at then is there's the computer screen And then now you can see it has just got a bit of a glare there, but it's connected to this magic forceometer. When I'm holding it vertically, it should register 0. But when I'm holding it about yay, it's close enough. So what I'm going to do is put this sucker on there, and hopefully it will say a number dancing around 1.23. And look at that, 1.3-ish. All right. So it's ish. It ain't perfect, but that magic forceometer is calling it 1.3. So that skill is something I want you to know how to do. So the weight of this object, it said, was around 1.3-ish newtons, right? What did it say? 1.3. Let me write that down. 1.31, 1.32-ish. I'm going to call it that, 1.32-ish. Okay, all I did was just write that down. The forceometer says 1.32-ish newtons. Okay, now the next thing I'm going to do is make a drawing similar to this one, but for when that item is submerged in the aquarium, which you can see is still right there. I'm going to submerge it in aquarium here in just a bit. If this then is the aquarium, so I'll just draw the water surface. This is the string with, I don't know, the item taped to it. Like that, whatever, who cares? Tried to draw it like yay-ish. By yay. So what? Okay, so how many arrows do you see on this guy? How many arrows do you? 3. You see 3, don't you? 1 is the planet Earth doesn't turn itself off. There's FG. The other one is the force of the rope, which is what we will call tension. Okay, that's what this spring scale forceometer just measured as 1.32 when it was in air. But when it's in water, it won't be that anymore, because there is also an upwards FB. All right. So what that spring scale will read is gravity minus the buoyant force, and that's what you're going to do the math to predict. All right. When it's held in place, it still is just like life. Everything adds up to nothing. The sum of the forces in the y equals may will go away because it's not moving, so that equals 0. There are 2 positive forces, the 2 that are up, tension and buoyancy. Those 2 I will subtract gravity from, and it will equal, again, the number of days I've been to school this year. Okay, so to solve for that force of tension, which is what we would say, wow, this thing apparently weighs something different. Holding it up by a scale, that force of tension is what you're solving for. That force of tension, you push the plus button for gravity, you push the minus button for buoyancy to move it over. So that's plus, that's minus, okay? So here, let me give myself a little more room here. That force of tension then is force of gravity minus the buoyant force, okay? Now, the force of gravity, you all know the planet Earth doesn't treat this thing any differently just because it's underwater. In fact, the joke I use is the planet Earth is stupid. It does not even know this item is underwater. So it treats everything exactly the same. It's very democratic. So I will just simply call mg the force of gravity, because that's what it is. From that, I'll subtract the buoyant force. Now, hopefully you remember the formula for a buoyant force. It is the density, not of the piece of metal, of the liquid it is submerged in, which is H2O. The density of the H2O times whatever gravity we're hanging out on times the volume that is submerged. Okay. Rho V is the mass of the H2O that was pushed out of the way by that piece of metal. G is what turns it into a force. So there's mg. All right. So this is the formula we want to know. Now you know the mass of the object in kgs, it's 0.1237. You know the planet Earth, 9.8. You know the density of high quality H2O was 1,000. You know that's still 9.8. The only number you don't know is the volume of that object that is end up underwater, the volume that's submerged. And so in order to get that volume that's submerged, what I'm going to do is use something that looks like a tin can with a spout on it. The reason why it looks like a tin can with a spout on it is because it's a tin can with a spout on it. Actually, it's aluminum. Sorry. But all it is just an aluminum can with a little spout right there. Okay? What I'm going to do is block the spout, put it underwater, and I'm going to fill that can up to above the spout. Okay? So now what I'm going to do is basically let that water drain until, is it, nope, it's not quite full enough yet, sorry. Let me let the water drain until it gets rid of all the water that is above the spout. All right, so now once that's done dripping, can you tell the surface in that of water in that can is such that it's right level with here, and if I displace any more water, it will be pushed out. So we're basically going back to elementary school, and we're going to see the volume of this guy. We're going to measure it using what's called the displacement method. So I'm just going to stick this sucker down in there. As it moves down in there, it pushes water out of the way. The amount of water it pushes out of the way is the volume of the entire object because it's completely submerged. You can see it's completely submerged under there. It pushed water out of the spout, and the amount of water it pushed out of the way is that, right? So if I can quantify that amount of water, I can get the volume of that item, and that's the amount that is submerged. So what we're going to do, go back to our happy chemistry class, remind ourselves how to read a graduated cylinder, which I'm sure you probably can't see in the camera right there, but I will try to make it somewhat more visible. I don't know, but you can see the individual tick marks. What I'll do is read it for you as I pour this in there. I'm going to have to do it probably in 2 steps because that right there, that right there is, let me pour a little bit of it back. All right. That right there is the maximus capacitus of this particular graduated cylinder. That's 25 mLs. Okay. So this graduated cylinder has already got 25 mLs in it. So I'm going to pour that back into the main aquarium. And then I'm going to add the rest of this to that number 25 to get the total. It's just, darn it, the graduated cylinder wasn't quite big enough. Okay. So where this ended up And this particular reading is just above the 20. So it's like 21, 22-ish, 21-ish. All right. So the volume submerged of that particular item was, the initial was 25 mLs, and then to that I have to add this other 21 mLs, because remember I had to do it twice. So 25 plus 21 mLs, I'm looking at 46 mLs. Okay. All right, so here we go. We're going to keep doing the math here. Keep doing the math. So the equation again was the force of tension, which is what we're solving for, is equal to mg minus rho H2O G V sub. All right? The volume that was submerged. Now, the volume that was submerged, we just said, is 46 milliliters. Hopefully your chemistry teacher reminds you, or your just knowledge of density tells you that's the same thing as 46 cubic centimeters. They're identical. A milliliter and a cubic centimeter are the exact same thing. All right? And something else you all already know. Remember this conversion, 46 CM3s, a CM to an M. You all know there's 100 in one, right? But this is a cubic centimeter. So what I have to do is cube everything inside that parenthesis. So the cube applies to the CMs, and that kills the cubic centimeters. The cube applies to the number 100. So it's 100 cubed, which means it's a million, right? So I'm going to move it over 6 places to the left to make it a smaller number. So in cubic centimeters, 2 meters, this ends up being, you can write the exact same number. It's 46. But it's times 10 to the negative 6th cubic meters. That's the number we're going to use, 46 times 10 to the negative 6th cubic meters. All right, you can use that number. That's the happy number for the volume. Please remember how to do that conversion. All right, so now we can make our prediction. The force of tension when I hold that sucker underwater, it should read something like this. That M, remember what we said the mass was in kgs, 0.1237. That's way too many digits. I'm just going to call it 0.124 kgs. I'm going to multiply that by 9.8 meters per second squared, okay? That quantity is mg. From that, I'm going to subtract, and I ran out of room this way. I'm going to just come down here. This is all the same equation. From that, I'm going to subtract the density of water, 1,000 kilograms per cubic meter, times the same 9.8 meters per second squared. I'm going to multiply that again by the number we just obtained, 46 e negative 6 cubic meters. Okay, so this math again is what I'm going to do all at once, and I want you to do the math all at once. Please do not baby step your way through this calculation. Do the math all at once. All right, and so what I'm going to show you is 0.124 times 9.8. All right. From that, I'm going to subtract. And if you want to put these in parentheses, you can. You don't have to. It knows to push the times button and the multiply button before the subtract button. But if it makes you feel better, let me put that in parentheses. Second insert parenthesis, boom, parentheses. So there's the first part of the equation, 0.124 times 9.8. The next thing I'm going to do is push the minus button, open another parenthesis, which again, you really don't need to, but I'm going to then subtract this quantity, 1,000 times 9.8 times 46e negative 6. Boom, and close the parentheses. All right, do the math all at once. Bang. 0.7644 is what this item says. The tension that we're predicting, the apparent weight, 0.764, and it said another digit. That's plenty. Newtons. All right, 0.764 newtons. That ought to be what this forceometer registers as the weight of this guy when it is submerged in the aquarium. All right, and so I can go back to our aquarium here, maybe get it so that you can see both the aquarium and the reading on the forceometer simultaneously. Okay, and the prediction 0.764. Okay, so that's all right there. I'm going to put this water back in, not that we really need it, but there it is to get it out of the way. I'm going to take this out, and I'm just going to set it down for now to get it out of the way. I'm going to pour this water back into the aquarium just to get it out the way. All right, and then I'm going to show you what this will say when we put it all together here. All right, so now you can see again it's hanging at 0.13-ish, 0.1. What did we say it was? 0.132 is what the forceometer said. It should drop down to 0.764 or somewhere very near there. It won't be perfect, but hopefully you can see that number decreasing, and now it's completely submerged, and you can see, okay, it's 0.86 and 0.87-ish instead of 0.76. And so we're off by what, 1/10 of a Newton, which I don't think is too terrible. 1/10 of 1 Newton, for gosh sakes. So this is 0.863 is what it's saying. I'm going to call it 0.863 newtons. And so we're off by ish 0.1 newtons, which 1/10 of a Newton, folks, that ain't bad. I'll take it. All right, we have guessed the apparent weight of this guy. Now, what you guys are going to do is the math to guess the apparent weight of something. All right, what that something is, though, these numbers are going to be what you now need to write down. What I'm going to do is give you back some memories to back in the day, maybe from middle school. This box here, maybe you remember looking at things like that. Huh? Look at those. This class rocks. But these are samples of common ores for metals that you probably looked at in a middle school kind of earth science class. And they're all labeled. There is one in particular I'm going to have us do. It's labeled as ore number 7. It's not a big deal, but it's magnetite. All right, it's a very heavy, because you can see how big this item is. And I'm going to put it on the scale, and hopefully that scale will be visible, because you're going to need this number. 165.35. That should strike you as pretty darn big for something like that size. Okay, I mean, that's really all the bigger it is. So what do we say? Hopefully you wrote that down. 165.43, if anywhere in there. All right, so that number is a number you need to have written down. And with that, then you're going to need to be able to calculate what it would weigh in air, like I just started with on this video. Then you're going to need to be able to predict what it would weigh when you stick it underwater. And so I'm going to need to do the same thing I did with the piece of aluminum there. And that means I need more water in here to make sure it goes above the surface and see how it's peeing. That means we're above the surface where it needs to be. All right, so then boom, what I'm going to do is take that excess water that is above the surface there, put it back. All right, so what we're going to do is just put this sucker underwater the same way we did the other one. So here it is. All I'm going to do is the same thing I did there. And that item is pushing all that water out the way. As soon as I know what that is, I can measure the volume of that water. I can calculate the weight of that water. And the weight of that water is the buoyant force, which is equal to the upwards force it will apply, which will be what we subtract from the weight that you just calculated based it being on the scale. Okay, so I'm going to have to measure that quantity of high quality H2O. And so hopefully I can do this in one pour, but it looks like this will be a little bigger than 25. Okay, so right there we're at 25 mLs. So I'm going to have to get rid of that. That was 25, and there's only a very small amount left here. So this volume will be 25 plus 25 plus 10, 11, 12, 25 plus 12. All right, that's 37. So the volume, 37 mLs. Okay, the volume that was submerged, 37 mLs. The mass, this thing said, was what, 160 something? The mass was 165 point. This is reading 7.3 now. You probably wrote a number slightly smaller than that down for grams. So, okay, based on that, what you're going to do is tell me the apparent weight of this. What will this force sensor, that screen right there, what will it say when this is held underwater in the aquarium? All right, so you're guessing your apparent weight is what that's called. So that is the last of the activities that deal with fluid statics. All right, and so you're doing that along with the life raft activity this weekend. So those are two things that you're doing over Labor Day. Okay, I didn't give you two different numbers for this particular one. For odd students or even students, it doesn't matter. But okay, so that's the activities you're doing. The life raft, guess your apparent weight. All right, and again, I'm sorry I can't be there in person. I do feel a little better today, but it's weird now when I breathe. If I breathe too deeply, it feels like when you breathe really cold air and it just kind of burns on your way down. So I don't think it's good if you feel like your lungs are on fire. That's bad. But anyway, that's why I study physics, because biology just don't make no sense. But anyway, stay afloat.